Okay, this is Regents Chemistry Review, Session 3, and we're going to focus on bonding and periodic table today. Remember, this is review by example. So what are some general characteristics that we can make about bonding? Let's start with ionic. First of all, you should recall that it's between a metal and a non-metal, and that there is a transfer of electrons. Those are the two biggest things. Remember that metals tend to lose electrons and form positive ions. When you lose weight, you become happy. Nonmetals tend to gain electrons, and when you gain electrons, you become negative, so they form negative ions. So when we have these positive and negative ions, we then have an attractive force between the two elements, and a bond is formed. So let's look at an example of sodium chloride. Na has 1 valence electron, Cl has 7 valence electrons. So Na gives up its electron to Cl, thus causing it to become a positively charged ion, and chlorine a negatively charged ion. Okay, so Na, with its positive charge, is then attracted to chlorine with its negative charge, and a bond is formed. For covalent, this is kind of synonymous for purposes of this class with molecular. We have nonmetals only involved, nonmetals only, and there is a sharing of electrons, not a direct transfer. So hydrogen has 1 valence electron and chlorine's got 7. No brackets, no charge, they share. Everybody's happy because chlorine now has 8 in its valence shell, and hydrogen is happy because it has 2 in its valence shell. Remember, hydrogen is the exception to the octet rule. It does not want 8, it only wants 2. The other type of bonding that probably warrants mentioning is metallic, and that's involved with metal atoms only. And there really isn't much to show with this. I could have a bunch of positively charged silver atoms and we have mobile electrons constantly moving in metallic bonds, which makes them very good conductors of heat and electricity. So let's review bonding by example. In H2, I have an electronegativity difference of 0 because there's 2 of them. If my electronegativity difference is equal to 0, it is going to be nonpolar. And the reason it's nonpolar is due to its symmetry. So this is not a dipole. If I were to draw the dash structure model, it's just simply H bonded to H. For the electron dot model, you know each H has 1 electron. I'll show it by X and a dot. They're sharing, they're happy, they're 2. The shape is linear, and they are symmetrical. Or it is symmetrical, which is why it is nonpolar. Nonpolar lends itself to being symmetrical. Polar is asymmetrical. NaCl, the electronegativity difference is going to be Na is 0.9 and Cl is 3.2. So this is going to be a difference of 2.3. So my electronegativity difference, the difference between the two numbers is 2.3. So this is definitely going to be ionic. I knew that before I even did the electronegativity difference because I had a metal and a non-metal. And there's only one structure that you can draw, and I already drew it for you. It was Na. It gave up its electron. It was positively charged, bonded to Cl. Which has a negative charge. Must have brackets and charge on ionic compounds. MgCl2, Mg is 1.3, and Cl is 3.2. Be a difference of 1.9. So this is also going to be ionic, but we knew that due to a metal and a non-metal. Now here, Mg wants to give up 2 electrons. It's 2 in its valence shell. And it's going to give them both up. So it's going to have a +2 charge. One of them is going to Cl. And remember that you have 2 Cl's in this compound. So this assumes a -1 charge. The other electron is going to go to the other Cl. And it's going to assume a negative charge. So you have 2 Cl's, each with a negative charge, and the Mg, which gave up both charges. Okay, let's look at water. The electronegativity difference, H is 2.2, and oxygen is 3.4. So that's going to give us a difference of 1.2. So this is going to be polar, and it is going to have a dipole, meaning it's going to have some pull, an unequal charge distribution. That's what dipole means. The dash structure is going to be H2O. The electron dot structure, well, you know that water has 6 electrons. Oxygen has 6 electrons. H comes in here with 1, H comes in here with 1, and there are 2 lone pairs. It is a bent molecule, and it's bent due to the lone pair repulsions happening on the oxygen, and it is asymmetrical. You must know water is polar, because that brings up a whole other topic of like dissolves like. So if something doesn't dissolve in water, then it does not have a similar polarity. It's probably nonpolar if it won't dissolve in water. CO2. C has got an electronegativity of 2.6. O we said was 3.4. So that's going to give us a difference of 0.8. This is also polar. However, this is not a dipole. And the reason being is it is symmetrical in shape. It looks like this. If we were to draw it out with the electrons, here's the 4 from the C, and then the 2 from the O's, and each O has 6, so there are 2 lone pairs of electrons. I'm going to draw that down here. because it's really important that you memorize water and carbon dioxide. So here's the 4 for the carbon dioxide, and then oxygen has got 6. So remember, 2 electrons, in this case where you have this and this, that's equal to a bond line. So when you have in the middle there the 2 X's and the 2 dots, that's equivalent to a double bond. And you can see that everyone's happy here because this oxygen now has 8, 2, 4, 6, 8. This oxygen now has 8, 2, 4, 6, 8. And the carbon in the middle has 8 because it's sharing those 8. The shape of the molecule is linear, and it is symmetrical, meaning it has an even charge distribution. You might want to write that down somewhere. Symmetrical is equal charge distribution, and asymmetrical is unequal charge distribution, meaning one side of the molecule has more pull or more charge than the other. NH3, let's move on. Electronegativity difference. N is 3.0, H is 2.2, so that gives us a 0.8 difference. This is polar. Oh, why did I say this was polar? Oh, the bond type. Okay, let me clarify something here. The bond between the C and the O, this little individual bond right here is polar. So the bond type is polar, but the overall molecule is nonpolar. And you have to be careful the way they read the question. Okay? So this is also polar, but it is asymmetrical in shape, so this is also a dipole for the NH3. Because when I draw it, I've got a lone pair here, NH3. This is what it looks like. Okay, I can put my lone pairs here, but I didn't. But that has lone pairs on it as well. Now if I were to draw the whole dot diagram, you'd see here's the N, here are the ones from the rest of the N. N's got 5, here comes an H, here comes an H, and here comes an H. Okay? This is pyramidal because you have the lone pair at the top. And it is asymmetrical. CCl4. C is 2.6. Cl is 3.2. So that gives us 0.6. The bond type between the C and the Cl is polar. The overall molecule is not a dipole. And the reason being is because it is symmetrical in shape. Cl, 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 Cl. So this is symmetrical, which means it's got equal charge distribution. So the pull of the Cl in the 4 different directions, north, south, east, and west cancel out, making it a nonpolar molecule. If I examine one bond, though, between the Cl and the C, it is polar. If I were to draw the electron dot structure, here's my 4 valence electrons for my Cls, my carbons, and then in comes my Cl with 7 on each side. And it is tetrahedral. Anytime carbon forms 4 bonds, it's going to be tetrahedral in shape. Using electronegativity differences, arrange the following 4 compounds in order of increasing ionic character. So we have to look all of these up. So let's write them down. We've got KBr, we've got ACl3, Li2O, and NaI. So K is 0.8, and we've got 3.2 for Br. So then my electronegativity difference is equal to 2.2. For Al, I've got 1.6, and for Cl, I've got 3.2, so that gives me a difference of 1.6. For Li2O, I've got Li is 1, and oxygen is 3.4, so that gives me a difference of 2.4. And for the last one, I've got 0.9 and 2.7, which gives me a difference of 1.8. So it says arrange them in order of increasing ionic character. So the smallest difference, AlCl3, is less than NaI, which is less than KBr, which is less than Li2O. So Li2O has the most ionic character as it has the greatest difference. Characteristics of types of bonds. Well, we went over this kind of already on the first page. Ionic is metal and nonmetal. I told you it was a transfer. So we got a transfer of electrons. Molecular substances are also called covalent. So these are nonmetals. And we have a sharing of electrons. Network solids are covalently bonded. They are nonmetals. These are extremely strong. Some examples are diamond, graphite, which are both carbon. So they're both allotropes of one another, which means that they have made up of the same thing, but they're arranged differently, so they have different chemical and physical properties. And SiO2, which is quartz or sand, is another one. Metallic bonding is neither. This is just with metal atoms only. And they are surrounded by I like to use the word sea of mobile electrons. Okay, let's review writing formulas. Write out the formula for iron 3 oxide. Whenever you see a Roman numeral immediately following an element, it's telling you the actual charge. So this is +3. So I don't even have to look this up. So Fe is the symbol for iron. It has a +3 charge. Oxygen, I go to my periodic table. I look up the oxidation state of oxygen. It's -2. And remember then, I drop and cross. The 3 comes here. The 2 comes here. So my formula is Fe2O3. Whenever I have a transition element involved, that is, an element in groups about 3 through 12 in that area, but they have to have multiple positive oxidation states. So you're talking in the middle of the periodic table, if an element's got more than one positive oxidation state, I need to use a Roman numeral to let me know which one I'm talking about. And when I write the name, I have to write it out. So if I were to write the name of this, it would be, as it is here, iron, Roman numeral 3, oxide. If I don't put the Roman numeral, I'm wrong. Write out the formula for aluminum nitrite. Aluminum is Al. It has a +3 charge. I get that from the periodic table. Nitrite is NO2 -1. So when I drop and cross, we don't write the 1. So it's Al. I have to put the NO2 in parentheses because I have to bring down this charge of 3. Aluminum nitrite. What are the oxidation numbers of each of the elements in the compound K2CrO4? K2CrO4. Oxygen is -2. We get that from the periodic table. This is a compound, so the net charge has to equal 0. If I have 4 oxygens, that gives me a net -8. Potassium from the periodic table can only be +1, and I have 2 of them, so that's a net +2. So what number is going to equal 0 here? I have -8 and +2, so this would have to be +6. +6 and +2 is +8, and -8 is 0. So +6 for the chromium. Using your understanding of bonding and atomic structure, plus the picture below, define the conditions that are characteristic of a coordinate covalent bond. Well, when we draw out just simply NH3 by itself, we know that N has 5 valence electrons, depicted by the 5 circles here. Then each H comes in with 1 electron. So this is happy, stable, content right now. NH3, N's got 8, each H has got 2. But now a 4th H decides it wants to join the party. So when it does that, it has to give up its 1 electron because it comes in without any electrons. There's already 2 here. So the 4th H comes in, and it now forms a positive ion because when you give up 1 electron, you form a positive ion. This is the coordinate covalent bond right there. That is the coordinate covalent bond. So how can we put this in words? A coordinate covalent bond is formed when one atom donates both electrons in a bond. Normally, each element brings 1 electron to share in a bond. Here, both electrons were provided by N, and the 4th H gave up its electron when it joined the structure. Identify each of the following reactions as synthesis, decomposition, single replacement, or double replacement. Any of you that have had me remember what we equate these to. Let's take them one at a time, just a quick review. So you've got Number 1, synthesis. Synthesis is like marriage, A plus B, two things coming together to form a union, AB. Decomposition, number 2, decomposition is like divorce. You take that union, AB, and you split it up into its constituents. Single replacement. Single replacement is the whole somebody's getting kicked to the curb story. You're going out with your boyfriend or girlfriend and a new hottie moves into town. So what happens is you never lower your standards, you always raise your standards. So here comes A. Here's you and your significant other, BC. You're a couple. And A is extremely hot, and A is going to kick B to the curb. B winds up by itself, and A is now with C. Now remember, when we're talking about single replacement reactions, we always use table J. Okay? Table J. The element pushing in has to be more reactive than the element it's pushing out. So the element pushing in has to be higher up on table J than the one that it's pushing out. Remember, we don't lower our standards, we raise our standards. Double replacement. Double replacement, unfortunately, is like swingers. You have two couples, AB, you and your significant other, and another couple, CD, and things just don't work out. You're incompatible, and A now forms a relationship with D, and C is going out with B. So basically partners are switched. So let's go and look at what's going on here. I have a compound, I have a compound. Al is now hooked up with OH, and Ca is now hooked up with SO4. Well, this is exactly what I was just talking about. This is double replacement. They switched partners. And the next one, Mg plus O2 yields MgO. This is marriage or synthesis. Don't write marriage on your Regents exam. H2 plus Fe3O4. Fe gets kicked to the curb, and H hooks up with O. This is single replacement. Somebody got kicked to the curb. You got to use table J to make sure the reaction's going to happen. And in the last one, Ag2O is splitting up. This is our decomposition or divorce. Alright, they want us to balance these equations. So I have two F's on the left, one F on the right. I've got two H's on the left, one on the right. So let's see, if I put a 2 here, that gives me two H's and it gives me two F's. However, I have three O's here. So this is a problem. So we want to balance our O's first. Let's put a 3 here. This now gives me 3 O's and 3 O's. I'm good. 3 times 2 is 6 H's. So I need 6 H's. So I'm going to put a 6 here. That means I need 6 F's. 6 F's. So if I put a 3 here, that gives me 3 times 2 is 6. So I have 3F2 plus 3H2O yields 6HF plus O3. What is the sum of the coefficients? Don't forget that this is an unspoken 1 here. 6, 7, 10, 13 is the sum of the coefficients. 13. Let's look at the next one. This contains a polyatomic. Whenever a polyatomic stays intact, that's a good thing. I have 3 here and 2 here. So that's not going to work. This is an odd and an even. We want the least common denominator. So the least common Multiple between 2 and 3 is 6. So if I make this a 2, 2 times 3 is 6NO3. If I make this a 3, 3 times 2 is 6NO3. And now I need 2Al here, 3Pb here, and the sum of my coefficients is 10. Complete each of the following reactions by writing the correct formulas for the products in words and symbols. Balance each equation, then identify what type of reaction it is. So we've got a whole lot going on here. Barium is Ba plus gold 3 chloride. Well, the symbol for gold is Au. The Roman numeral tells us it's plus 3. And Cl is for chlorine, and it's minus 1. So when I drop and cross, this becomes AuCl3. And that's going to yield, well, Ba is above Au on table J. So Au is going to get kicked to the curb, and Ba is going to hook up with Cl. So Ba's got a plus 2 charge, Cl is a minus 1 charge. When we drop and cross, it becomes BaCl2. So let's put this into words up here. This is gold plus barium chloride. Let's balance our equation. They asked us to do that. I have 3 Cl's here, 2 here. Least common multiple is 6. So I'm going to change this to a 3, change this to a 2. This needs to be a 3. This needs to be a 2. And somebody got kicked to the curb. So this is single replacement. All right, calcium hydroxide. Calcium is Ca. It's got a plus 2 charge. Hydroxide is a polyatomic ion found in table E. It's OH minus 1. So when I drop and cross, this 2 has to come down here, which means the OH has to go in parentheses, plus potassium nitrate. Potassium is K. Nitrate is a polyatomic, NO3, and these are both plus 1, minus 1. So they switch partners because these are two compounds. So they're going to switch partners. Ca is going to hook up. Ca's got a plus 2 charge with NO3 minus 1. So when we drop and cross, this 2 comes down here. Plus K plus 1 and OH minus 1. So those are good. We don't have to drop and cross on them. Let's balance. I have 2 NO3, so I'm going to put a 2 here. And I have 2 H's and 2 O's, so I'm going to put a 2 here. And I have 2 K's, so I have 2K, 2K, 2 NO3, 2 NO3, 2 O's, and 2 H's. 2 O's and 2 H's, so we're good. We're balanced. Again, I have a compound and a compound. They switch partners. K hooked up with OH, Ca hooked up with NO3. So this is double replacement. All right, let's review a little bit about the periodic table. Elements in the same group. Have the same number of valence electrons. This is really important. Therefore, they have similar properties. And they are going to bond in the same way. What do we know? We know by looking at table S, we know that electronegativity and ionization energy decrease down a group, and they increase across a period. Let's talk about that. Ionization energy. As we go down a group, we add principal energy levels, and therefore the outermost electrons are further from the nucleus. They are shielded by the individual principal energy levels. So as shielding increases, the attractive forces between the protons in the nucleus and the electrons in the outermost shell decrease, and it becomes very easy to pluck off that outermost electron. So ionization energy is the amount of energy needed to remove an electron, the outermost electron, and that decreases as we go down a group because the outermost electrons are further from the nucleus. Now, for something like sodium, which has an electron configuration of 281, that first ionization energy is going to be very small because we'll get rid of that last electron and be left with 8. If I tried to remove a second electron, you would see that that ionization energy would jump up very high because now we're violating the core electrons, and we don't want to give up any of the core electrons. Electronegativity decreases as we go down a group, again because the more principal energy levels you have, the further the nucleus is from electrons that are in a bond. So the bigger the molecule you are, the harder it is to have an attraction for another molecule's electrons. Atomic radius increases down a group because you are adding principal energy levels. Now let's talk about when we go across a period. When we go across a period, my ionization energy is going to increase, meaning it's going to be more difficult to remove an electron as we go from left to right across a period. Why? Because we're getting into non-metal territory, and non-metals don't like to give up electrons, they like to gain electrons. Not only that, you have an increased nuclear charge, so you have an increased attraction for those outermost electrons because you have more protons as you go across a group. Your ionic radius decreases as you go across a group because you have more nuclear charge tugging in on those electrons, attracting them toward the nucleus, and therefore everything gets snugged together and the radius decreases. Now, you don't have to memorize the trends. It's helpful that you understand what's going on, but the trends can be all verified by taking several elements and then looking up in Table S and looking them up and see what happens, what's going on with their electronegativity, their ionization energy, and their atomic radius. Okay, hopefully this was helpful, and next time we're going to review some math associated with chemistry.